The universe beckons, a vast and enigmatic expanse stretching beyond our comprehension. It is a realm of endless possibilities and profound mysteries. It calls to us across unfathomable distances, a siren song of starlight and cosmic wonder, inviting us to explore its hidden depths. Whispering tales of cosmic birth, stellar life, and galactic endings, the universe unfolds its epic narrative across billions of years. NASA has sent its mechanical emissaries into the void, tireless explorers venturing into the unknown reaches of space. Pushing the boundaries of what we know, these probes and telescopes are our eyes and ears in the cosmos, constantly expanding our understanding. Each discovery answers one question, illuminating a small corner of the cosmic tapestry, while posing a dozen more, revealing the infinite complexity and inherent mystery of the universe, reminding us that the cosmos is the ultimate, unsolved mystery, a puzzle box of unimaginable scale and intricacy. Our instruments now peer back to the very infancy of the universe, capturing glimpses of a time when everything was compressed into an infinitely small point, revealing the faint residual heat left over from the Big Bang, a whisper from the dawn of time. A cosmic afterglow that holds the secrets of our origins, a blueprint of the universe as it once was. But this ancient map contains strange, unexplained features, deviations from the expected pattern that pique our curiosity. Anomalies that challenge our understanding, forcing us to question our assumptions and refine our theories. Among these puzzles, one stands out, a particularly intriguing enigma that has captured the attention of cosmologists worldwide. A region of space colder than it should be, a cosmic anomaly that defies explanation. Defying our best models, this cold spot presents a significant challenge to our current understanding of the universe. This is the story of the CMB cold spot, a tale of scientific intrigue and cosmic mystery. A cosmic detective story that could change everything we know about the universe, potentially rewriting our understanding of the cosmos. Is it a random fluke, a statistical anomaly in the cosmic microwave background, or a signpost pointing to a far grander cosmos than we ever imagined? Could it be evidence of a multiverse, a collection of infinite universes beyond our own? The journey begins now, as we delve into the mysteries of the CMB cold spot and explore the profound implications it holds for our understanding of the universe. Imagine the universe in its absolute infancy, a time far beyond our everyday comprehension. It was a searing, brilliant inferno, unimaginably denser and hotter than the core of any star we observe today. This wasn't just heat, it was raw, unfettered energy. For nearly 380,000 years, light in its nascent form was effectively trapped. It was caught in a dense, swirling fog of elementary particles, unable to travel freely across the vast expanse that the universe would eventually become. Photons, the very essence of light, were in a constant state of scattering, unable to break free from this primordial soup. Then, as the universe gradually cooled, a monumental shift occurred. Atoms, the fundamental building blocks of matter, began to form, primarily hydrogen and helium. And as these atoms stabilized, the fog that had imprisoned light for eons finally cleared, marking a pivotal moment in cosmic history. The first light, no longer constrained, was released in a burst of cosmic radiation, embarking on an epic journey across the ever-expanding cosmos, traveling for billions upon billions of years. Stretched and redshifted by the relentless expansion of space itself, its wavelength elongated as the universe grew, this ancient light, once a blinding inferno, gradually transformed into the faint microwave radiation we now know as the cosmic microwave background, or CMB. The CMB is, in essence, a baby picture of the universe, a relic of its earliest observable state, a snapshot frozen in time from approximately 13.8 billion years ago, offering a glimpse into the conditions that prevailed shortly after the Big Bang. It permeates and fills the entire sky, surrounding us in all directions, providing compelling evidence that confirms the Big Bang theory as the most accurate model for the universe's origin and evolution. It offers a direct and invaluable glimpse into our deepest cosmic origins, allowing us to probe the conditions of the universe when it was only a fraction of its current age. Mapping the CMB with sophisticated instruments reveals a sky that is remarkably, almost perfectly, uniform in temperature across vast stretches of space, registering at approximately 2.7 degrees above absolute zero, the coldest possible temperature. However, with the aid of incredibly sensitive instruments, scientists have discovered the existence of tiny, subtle variations in this temperature. minuscule ripples and fluctuations, differing by only millionths of a degree from the average. These slightly warmer, hot spots and slightly cooler, cold spots regions represent the seeds of all future structure in the universe. The initial density fluctuations that gravity would later amplify, the slightly denser regions that, over billions of years, would coalesce and evolve into the galaxies we observe today, the birthplaces of stars, and ultimately, the formation of planetary systems like our own. The CMB is far more than just a relic of the early universe. It serves as the fundamental blueprint, the underlying framework for everything we observe in the cosmos today. And within this intricate blueprint, within this tapestry of cosmic information, there exists one particular anomaly that continues to intrigue and baffle scientists. One unusual feature stands out: the enigmatic cold spot. In 2004, astronomers using WMAP mapped the universe's earliest light, expecting a random pattern of hot and cold spots. But in the constellation Eridanus, they found something that shouldn't exist, a spot significantly colder and larger than any other. This cold spot was about 70 microkelvins colder, spanning a billion light-years. Its sheer improbability, odds of 1 in 2,000, made scientists take notice. Science thrives on anomalies, and this was one of the biggest ever found. Planck satellite data confirmed the cold spot's existence with even greater precision. It was real, a genuine feature of our universe, imprinted on the oldest light. The mystery deepened. What could cause such a massive cold imprint? The discovery opened a floodgate of questions and set astronomers on a quest for answers. Was it a fluke or something far stranger? The search for an explanation began. When scientists first stumbled upon the CMB cold spot, a region of unusually low temperature in the cosmic microwave background, they knew they were facing a cosmic puzzle. The initial reaction was to seek out a conventional explanation, something within our current understanding of the universe. The most obvious suspect? A giant void in space. These voids are vast regions, almost entirely devoid of galaxies and matter. The integrated Sachs-Wolf effect suggests that as CMB light, the afterglow of the Big Bang, passes through a vast empty region, a cosmic void stretching across billions of light-years, it loses energy due to the gravitational effects, appearing colder to our telescopes. If a supervoid, an exceptionally large void, caused the cold spot, we should be able to see it by meticulously mapping the distribution of galaxies in that direction, essentially looking for a gaping hole in the cosmic web. And indeed, astronomers found a supervoid, one of the largest ever discovered, a truly colossal emptiness, stretching an incredible 1.8 billion light-years across. It seemed for a moment like the perfect solution, a neat and tidy explanation for the cold spot's existence. But, frustratingly, the void wasn't empty enough. The observed density of matter within the void wasn't low enough to explain the entire temperature drop associated with the cold spot. It could only account for about 10 to 20% of the observed coldness. The mystery remained, stubbornly resisting a simple answer. The universe, as always, refused to give up its secrets so easily, holding on to its enigmas with a cosmic grip. If the void, despite its immense size, wasn't the full answer, if it only accounted for a fraction of the temperature anomaly, what else? What other exotic or unknown phenomena could explain the cold spot? The search for a deeper, more profound cause continued, pushing the boundaries of our understanding. Was there something even stranger at play? Some exotic physics or interaction that we hadn't yet considered? The next theory, a far more radical proposition, would take us beyond the boundaries of our own observable universe, venturing into speculative territory. Into the realm of the multiverse, the hypothetical existence of countless other universes beyond our own. With the supervoid theory falling short, some cosmologists asked a radical question. What if the cold spot is the mark of an encounter with another universe? The theory of eternal inflation suggests our universe is just one bubble in a vast multiverse. If two bubble universes collided in their infancy, the shockwaves could create a cold, underdense region, imprinted on the CMB as the cold spot. This cosmic bruise theory elegantly explains both the cold spot and the supervoid within it. The collision would have created a region with less matter from the very beginning, leaving a lasting mark. In this view, the supervoid and the cold spot are both symptoms of a profound event, an ancient bump in the cosmic night. If true, the cold spot is the first observational evidence that we are part of a much larger multiverse. It's a breathtaking idea, challenging everything we know about reality. But can we test it? The multiverse isn't just science fiction. It emerges from leading theories like string theory and eternal inflation. In this view, our universe is one bubble among countless others, each with its own laws and possibilities. The cosmic bruise theory makes a bold prediction. A universe collision should leave specific patterns in the polarization of the CMB within the cold spot. Detecting these faint, swirling patterns would be like finding the fingerprints of another universe. For the first time, we might have a way to empirically test the existence of other universes. Such a discovery would be a paradigm shift, redefining our place in the cosmos. Our observable universe would become just a tiny part of a much larger reality. The cold spot could be the key to answering the ultimate question. Are we alone, even at the level of universes? The implications would be profound. The search for evidence continues. Science demands skepticism and rigorous testing of every bold idea. Many cosmologists argue the cold spot could simply be a statistical fluke, a rare but not impossible outlier. Simulations suggest such anomalies can occur by chance, perhaps as often as 1 in 50 times. It's rare enough to be interesting, but not so rare as to require a new universe to explain it. Other theories propose the cold spot could be a cosmic defect, a texture formed during the universe's earliest moments. These tangled knots in space-time could leave cold imprints on the CMB. The debate is a perfect example of science in action, anomaly versus Occam's razor. The only way to settle it is with more and better data. Future telescopes will map the CMB and its polarization in greater detail, searching for the truth. The mystery endures, driving us to look deeper. The cold spot is more than a cold patch in the sky. It's a crossroads for cosmology. If it's a statistical fluke, it still pushes our models and techniques to new heights. If the supervoid explanation is correct, it could reveal new physics about dark energy and the universe's structure. But if the multiverse theory is proven, it would fundamentally alter our perception of reality. Our universe would become just one of many, and the Big Bang just one beginning among countless others. The cold spot forces us to confront the biggest questions. What are our origins? What are the laws of reality? Are we truly alone? Whatever the answer, the journey itself is invaluable. The universe's grandest secrets are often hidden in the faintest, coldest clues. The search continues. The story of the cold spot is far from over. New telescopes and missions are being designed to probe its mysteries, mapping the CMB's polarization and the universe's structure in unprecedented detail. Projects like LIGHTBIRD and the Rubin Observatory will help us test the cosmic collision theory and map the supervoid with clarity. This two-pronged approach is our best hope for solving the puzzle. The quest to understand the cold spot embodies the spirit of scientific inquiry, curiosity, evidence, and the courage to ask, what if? Whatever the answer, the search will enrich us, expand our perspective, and push the boundaries of knowledge. The universe is full of unanswered questions, and that is its greatest gift. The cosmos awaits,